Let's move on with Chapter 22 stuff. Remaining parts of question 2215 will be dealt with tomorrow in discussion class. Be there. And tomorrow, reminder, special quiz 2 due. So we will proceed with the quantitative aspects of electrochemistry. Just like we did with acid-base chemistry. First, the qualitative stuff. Learn how to write equations for acid-base reactions. Here we learn how to develop equations for redox reactions. After we do that, we can analyze electrochemical systems quantitatively, like with the acid-base stuff. After we learn how to write equations for acid-base reactions, then we were in position to learn how to analyze quantitatively equilibrium systems of Bronsted-Lowry acids and bases. There are two aspects of electrochemical arithmetic: Faraday's law and the Nernst equation. With the Nernst equation, you will see extended use of the information in our table of half reactions. Faraday's law, in the main, is a consideration applied to electrolysis processes. For example, many metals are produced by electrolyzing a molten salt of the metal in the oxidized state, like a metal oxide, where the metal's in a positive oxidation state. Melt the metal oxide, run a current through it, and based on Faraday's law, determine how much of the metal can be produced at the cathode, the electrode at which reduction occurs. If we electrolyze a molten metal oxide with production of the metal at the cathode, what are we going to make at the anode? What will we make at the anode? We're electrolyzing a molten metal oxide, producing the metal at the cathode. The anode's the electrode at which oxidation occurs. What are we going to make at the anode? Well, you can make one statement which is always correct. The most readily oxidizable component of the system. Fair enough? Now, if that component is the anion of the molten metal salt, and we're electrolyzing a molten metal oxide, what are we going to make at the anode? Oxygen gas. You betcha. As a practical example, elemental sodium, very reactive stuff. Consequence, practically speaking, it can only be produced by electrolysis as opposed to chemical reaction. Sodium chloride, molten, is electrolyzed. Makes sodium at the cathode. And the other product is also commercially quite important. What will we make at the anode? What do you expect to make at the anode if we electrolyze molten sodium chloride? Chlorine gas. important stuff. Has many industrial uses. Now then, to understand Faraday's law, first some definitions. Electrochemically, the energy unit joule has its electrochemical equivalent of volt, electrochemical potential, times Coulomb, which is charge. V volt is also fundamentally current flow times the time for which the current does flow, or current times the time for which the current does flow. So a joule is volts times coulombs, or volts times amps times seconds. Faraday is simply a term coined in honor of Michael Faraday, and it is the total charge borne by 1 mole of electrons. Well, 1 electron, since it's the smallest known negative particle, is identified as the species with unit charge. You learned this in 2045, I trust. And the charge on a single electron is 1.6 times 10 to the minus 19 coulombs. You remember the famous experiment that was done to identify that quantity? We talked about this in 2045, I think. Millikan's oil drop experiment. 1908. Long time ago, over 100 years ago. Nobel Prize winning experiment. So, if we take the charge on a single electron and multiply it by a mole of electrons, we get to Faraday. 96,500 3 sig figs coulombs per mole of electron. Here's Faraday's law, algebraically expressed. Mass of material transferred, produced, well, let's say produced. If, for example, I apply Faraday's law to the electrolysis of molten sodium chloride, then with Faraday's law I can calculate, after running the current for a particular amount of time, I can calculate the amount of sodium I expect to produce at the cathode, as well as the amount of chlorine I expect to produce at the anode. Q is charge in coulombs. Squiggly fancy M is formula mass, molar mass if you prefer. F is the Faraday, and N is moles of electrons transferred, or moles of electrons required for the process. How do we get N? N comes strictly and exclusively from the equation for the reaction. You remember when we talked about getting units for equilibrium constants? If the equilibrium constant is calculated from thermodynamic properties for the system? Because when you calculate an equilibrium constant using thermodynamic properties, you get a unitless value, a unitless quantity. How do we get units for an equilibrium reaction? By looking at the reaction itself. That's the only way to do it. Same general idea here. If you want to know what the value for N is, you have to pay attention to the redox process which is being conducted. If, for example, we're reducing copper in the +2 oxidation state with the intention of making copper metal at the cathode, then per mole of copper +2 we need 2 moles of electrons, so N is 2. Nothing fancy about this. You know how to get N, for example, in the coupling process. After you adjust the coefficients appropriately so that the summation of the oxidation half reaction with the reduction half reaction gives 0 net electricity, the value for electrons transferred in the oxidation reaction, which is equal to the value or quantity of electrons transferred in the reduction reaction, that's N. Now then, You all good at dimensional analysis? Because the only way to really do problems with Faraday's law, the only way to really do successfully calculations in any science class, where the data which you are processing always has units, is by unit or dimensional analysis. What's the essence of dimensional analysis? Again, also called unit analysis. The essence of such is to write a setup. One single setup, which contains all the arithmetic steps that you have to do. All the multiplications, all the divisions, a collection of factors. The essence of dimensional analysis is to construct this setup so that if you perform the indicated arithmetic on the units for the quantities contained in the setup which you have written, what will you get? What do you get?
A desired unit.
You will get the units which the statement of the question or the problem demand. And if you don't write a setup which fulfills this requirement, I don't care what you do with the numbers won't have any meaning at all. How tall is Ralph? 46. How much do you weigh? 3,012,000. What the hell? This means nothing, because it has no units. If you put units on it, then it has meaning. So, I think the best way to get at appreciating this is to take a look at some problems. There are some questions and corresponding answers offered on pages 19 and 20 in Chapter 22. One about the electrolysis of a silver nitrate solution. How much silver can we make? Well, notice that for this consideration, the first thing you want to do is to recognize that for the production of silver from silver ion, N has got to be 1. Because the charge on oxidized silver, or silver ion, is plus 1. And we carry on to the top of page 20. 2220. About 1/3 of the way down the page, we're talking about a battery being capable of delivering a 1.00 amp current. The battery is fabricated from the oxidation of zinc. I'm pretty sure this is the way flashlight batteries are made, or at least some types of flashlight batteries. Zinc with I'm pretty sure a manganese oxide paste, manganese dioxide paste. And the manganese dioxide oxidizes the zinc. The electricity for that transformation is channeled through an external circuit. How do you make the electricity pass? How do you go about getting zinc to be oxidized in this kind of battery? You know what a battery looks like? It's got a button at the top, doesn't it? Battery. And then the bottom plate of the battery, at least most batteries are designed this way, is the other electrode. Electrode at the top, electrode at the bottom. How do you get the redox reaction in the battery to take place? And at the same time get electricity to be liberated by the redox reaction in the battery that you can use to make the bulb in your flashlight light. You connect the electrodes, don't you? Right. That's the way the flashlight's designed, or any other gadget that runs on battery power. And in completing the circuit that's completed goes through the bulb in the flashlight, causing the flashlight bulb to glow. Now then, this question states, how long will the battery operate if it contains, if it's fabricated from 2.50 grams of zinc? Rather than saying it contains, I should have wrote if it's fabricated from, made from. Well, the arithmetic is there shown regarding how long the battery will last. About 2 hours. Now then, With that, let's go to question 2218, which is a takeoff on this zinc fabricated battery, and ask the question, if we want to make a similar battery, a battery which will deliver the same current, 1.00 amps, and last for the same amount of time, 2.05 hours. But we want to make the battery from aluminum rather than zinc. Question is, how much aluminum? So what we have to do to wrestle with question 18 is to relate moles of aluminum to moles of zinc. No more, no less. How are we going to do this? Now, what the poor student does at this stage of the game is to go grab Faraday's equation and say, now, what do I plug into here to answer the question? And the answer is, I have no idea. Electrochemically speaking, how do we relate moles of aluminum to moles of zinc?
Moles of electrons.
Moles of electrons. Now then, what's the only positive oxidation state shown by zinc? And the only positive oxidation state shown by aluminum? 3 plus. So if a mole of aluminum is oxidized, will I get more electricity, the same amount of electricity, or less electricity than oxidizing a mole of zinc? How much more? I don't like percents, but your answer is okay. How about 3/2 times as much? Will you buy that? Good. So we'll write down this to start constructing the setup. Why do I write this factor first? Am I not trying to find out how many moles of aluminum are required to build this battery? Is that what I'm trying to find out? Then that's the first factor to write down. I will tell you flatly that I've not yet seen a textbook which knows how to do dimensional analysis properly. Every damn one of them does it backwards. That's pretty stupid. Now, of course, the problems they use are easily dealt with from this backwards fashion. But if I write the problems, then you're going to have one hell of a mess. What are we going to write next factor?
Moles of electrons per moles of zinc.
Moles of electrons per moles of zinc. Do I write 1 mole of Zn per 2 moles of electrons, or 2 moles of electrons per mole of zinc? Because my horse sense tells me I want to relate moles of aluminum to moles of zinc, and I got to eliminate moles of electrons as a unit quantity from this setup that I am writing. And there's dimensional analysis already in operation. Now then, the question above, to which this question relates, identifies the quantity of zinc used to make the battery as 2.50 grams. Is that right? I'm not looking at it. I think it's 2.50 grams. Okay. So now our horse sense should tell us I've got to relate moles of zinc to a mass quantity of zinc in the unit grams. What property of every substance allows us to make a connection between moles of the substance and mass in grams of the substance? Formula mass. So I get out my periodic table. And I write 1 mole zinc per 65.4 grams zinc. I think that's right. You got a periodic table in the notes. This periodic table doesn't have formula mass information. Is that it? Yeah, okay. And there goes moles of zinc. And how many grams of zinc did I use to build the battery in question? 2.50 grams. Look at the units. Do the units, as things stand, generated by this setup, become moles of aluminum and that's it? And is this setup obviously based on the information for the consideration at hand? You betcha. So guess what? This setup's got to be right, it can't be wrong. If you know how to do dimensional analysis, you can solve problems which operate on data that you've never heard of before. Squiggles per scratch. Who cares? Squiggles cube per scratch to the 3/2. Who cares? If you know how to do dimensional analysis, you can solve the problem. Now we'll do the arithmetic. Get 0.0255 moles of aluminum. Is this mole quantity of aluminum a greater mole quantity or a smaller mole quantity than moles of zinc in the 2.5 grams of zinc? A greater mole quantity or a smaller mole quantity than the moles of zinc in 2.5 grams of zinc? This is smaller, isn't it? Why is that true? Did we not start by realizing that from a mole of aluminum I get 3 moles of electrons, but from a mole of zinc only 2? All right? Now then, if I calculate mass of aluminum, I will calculate a mass quantity which compares how to 2.5 grams? Smaller, bigger, a good deal bigger, a good deal smaller? Well, if I want a mass to mole relationship for aluminum, I need the formula mass of aluminum, don't I? That's 27.0 grams per mole, isn't it? And I've already recognized I have fewer moles of aluminum than I have moles of zinc. And I've now recognized that the formula mass of aluminum is less than half the formula mass of zinc, have I not? So I already know, without even doing any arithmetic, if I convert this to grams, I'm going to get a lot smaller number than 2.5 grams. And that's the kind of thinking you want to do before you just start plugging numbers into your push-button device or reaching for this recipe. All right, we go to 19. '19 involves the electrolysis of a molten metal chloride with the general formula MCl3. What you're supposed to do is to take the data supplied with the statement of question 19 and see if you can figure out which metal is part of MCl3. Now then, what property of the metal will you have to compute to identify the metal? What is it? Formula mass. Good. Now then, formula mass is a ratio of mass in grams per mole of the metal, right? How much of this metal was produced by this electrolysis? 2.695 grams of M, whatever the M is. Why should I write this down first? Am I not trying to write a setup which gives me a relationship between mass in grams of the metal per mole of the metal? And already I've got mass in grams of the metal in the numerator of the setup I am beginning to construct. So I know I'm starting out correctly. That's the way to play the game. Now then, we've already recognized that for a redox process, what also do we need to know from an electricity standpoint? Moles of electrons. Well, tell me about moles of electrons. Does this general formula not identify the oxidation state for the metal? +3, isn't it? So now we have this information to use. I mean, we're all expected at this stage of the game to know that in a molten metal chloride, the oxidation state of the chlorine atom is -1. So the metal must have a +3 oxidation state. So with this, I ask, what factor should I next write?
3 moles of electrons per mole of metal.
Mm-hmm. Do you see now that as I look at the units and what I have so far written, I got mass in grams of the metal up top and moles of the metal in the denominator? I got to be on the right track. And dimensionally, what now must I eliminate as I continue to expand on this setup? Moles of electrons. All right. Based on what we've considered over there, what's the next factor I need to put down in my setup? What information over here relates directly to moles of electrons? What is it?
Amperes times second per moles of electron.
Tell me the quantity. What's it called? Give me a name. Faraday. Goody. 96,500 coulombs per moles of electrons. All right? Is that the way I want to write the Faraday, or do I want to invert the Faraday? Now I'm going to take the liberty of expanding coulombs into amps times seconds straight away. And there goes moles of electrons. Now then, the remaining information in question 19 says, I'm running this current for 25 minutes and it's a 10 amp current. What do I want to do with the 10 amp current? Multiply or divide? Don't you want to multiply and get amps squared, whatever the hell that would mean? And there goes amps. Now then, 25 minutes. Well, this is in seconds. I trust you can relate seconds to minutes.
Yes. 60 seconds.
How about that? 60 seconds in a minute. Should I write 60 seconds per minute or 1 minute per 60 seconds? Don't you like seconds squared? And there goes seconds. And now comes the 25 minutes. The remaining factor to be added to the setup, which will complete construction of the setup. Do I multiply or divide by the 25 minutes? Done. You do the arithmetic. You'll find out the metal is chromium. Now then, 2220. Well, let's write it over here. We're going to consider this time running a current of electricity. We're going to consider electrolyzing molten magnesium chloride. Same current, 10 amps. Same period of time for which to conduct the electrolysis, 25 minutes. So 20 says, would the mass of magnesium obtained be more or less mass mg this or this? Now I can write a setup to answer this. Do I have to? If I electrolyze the molten magnesium chloride with the same current for the same amount of time on a mole basis, will I make more moles, the same moles, or fewer moles of magnesium compared to the moles of chromium which I produced? If I'm going to make a mole of chromium by electrolyzing molten MCl3, per mole of chromium produced, how many moles of electricity must I supply? 33. But if I'm going to make a mole of magnesium, how many moles of electricity must I supply? 2. So I repeat my question. In running this electrolysis, same current, same amount of time, except that now I'm electrolyzing molten magnesium chloride. Will I make more moles or fewer moles of magnesium than I made of chromium? More, you're damn right. Because I don't need as much electricity to make a mole of magnesium. Since I only need 2/3 moles of electricity compared to moles of electricity required to make a mole of chromium. Now, will I make a mass of magnesium? Because I've already reckoned I'm making more moles of magnesium than moles of chromium, right? Will the mass of magnesium produced be smaller or larger than 2.695 grams? And I will tell you, we've already done the thinking necessary to answer this question when we talked about the aluminum and zinc problem. Smaller mass quantity of magnesium? Why do you say this? What's your reason for saying this? I'm listening. I'll make 1.5 times as many moles of magnesium. Right? 1.5 times as many moles of magnesium. How does the formula mass of magnesium compare to that of chromium? Is it less than half the formula mass of chromium? You're daggone right. So the mass quantity will be smaller than 2.695 grams. Enough said. On we go to the Nernst equation. Now, some comments. This is the Nernst equation in its most familiar form. It's derived in the notes. You're not responsible for the derivation. You're responsible for being able to use this expression correctly. Likely you've already recognized this expression is provided on our information sheet. And beware of the symbol Q. Because over here, Q means charge, and over here, it's squiggly Q, which means reaction quotient. These are problems we run into in science. We've identified so many different quantities, we've become less clever in creating symbols to represent these quantities. I think we should come up with, reaction quotient, so we use the funny Q. Now, I don't know why we continue or insist on using Q to represent charge. I think we ought to change that. But charge is more a quantity considered in physics class than it is in chemistry class, whereas reaction quotient is a quantity considered in chemistry class rather than physics class. Well, RQ is a capital Q, squiggly Q, and prettier than that. So I'll tell the physicists to change their symbol for charge to something else. Will they listen to me? Probably not. V volts, operating potential for the cell under any imaginable set of conditions is equal to E0 for the cell. That's the standard electrochemical potential, which we already know how to get by coupling half-cell reactions under standard state conditions. Minus 0.059 V times log of the reaction quotient divided by N. From where do we get N? Equation for the redox reaction. Question. Given that, and you see this on pages, in the notes you'll see on pages 2222 and 2223, and the discussion culminates at the top of 2224, a very common use of the Nernst equation is to evaluate equilibrium constants. So let's imagine I'm using the Nernst equation to evaluate an equilibrium constant. For example, again in the notes on page, where is it here? 2222, we're showing you how the formation constant for the complex ion copper-ammonia complex ion, how the formation constant for that complex ion can be evaluated by applying Nernst equation to data which you see in our half reaction table. Page 2223, you'll see another application of Nernst equation where electrochemical measurement is used to evaluate pH. So before we go on with what I was considering, take a look at the half reaction table. And see if you can recognize right off the bat how many half reactions could be used as part of a redox system, which is to serve the purpose of constructing a pH meter. Looking at the half reaction table? Notice that the half reaction table in the notes is far more extensive than the half reaction table on the info sheet. Because if I put all these half reactions on the info sheet would have to be 2 pages, or else I'd have to print the half reactions in really tiny print. And for people like me who don't have such wonderful eyesight anymore, I wouldn't be able to read the damn thing. Well, I'm selfish. I'm serving my purpose. So I'll limit the amount of half reactions I contain on the info sheet. I again ask, looking at the half reaction table in the notes, table 2, do you see that a whole bunch of different half reactions could be used as part of the overall redox system as the basis for construction of a pH meter? You see this to be a true statement? Mm-hmm. Do you believe that any half reaction which has got hydronium ion contained within is ever so obviously a potential component of an electrochemical system used to measure pH? How about hydroxide ion? Of course. A whole bunch of half reactions could be used. The half reaction, pardon me, the pH meter system considered in the notes is developed by coupling the zinc-zinc ion half reaction with the standard hydrogen electrode. Have you yet paid attention to the standard hydrogen electrode on the half reaction table? You remember how the standard hydrogen electrode comes about having an operating standard potential of 0? You remember our thermodynamic reference point for measurements made in solution? Ions, chapter 21 again, where by definition, forming the hydrated proton, hydrogen proton, at a pH of exactly 0.00, exactly 1 molar. All the thermodynamic properties for that formation are 0. Del G sub F super 0, del S sub F super 0, all that stuff. That's how the standard hydrogen electrode comes about having an E0 value of 0, because, arithmetically speaking, delta G0 is equal to minus NF E0, where N is moles of electrons transferred, F is the Faraday, and E0 is the standard electrochemical potential. That relationship's also on the information sheet. I don't expect you to memorize this stuff. What? Indeed, I want you to be able to use it. All right. Now then. Oh, we were mentioning the use of this to evaluate equilibrium constants. A very common, frequent use of the Nernst equation. If I use the Nernst equation to get me an equilibrium constant, like a formation constant for a complex ion, or a solubility product for a semi-soluble salt, or even Ka for an acid, or Kb for a base, or if you look at it, you can see you can get Kw for water from these half reactions. I'm using the Nernst equation to get a K value. What's E cell? I'm using the Nernst equation to get an equilibrium constant value. What's E cell? 0! The damn thing's in equilibrium, isn't it? This comes from the half reactions after they've been coupled appropriately. And Q will now be equal to? K. You betcha. That's all there is to it. All right, back to this system. For this system, which we've already considered, you may recall that the E0 value is plus 1.10 volts. All right? If I'm running this system, what's Q? This over this. So immediately I can recognize. You see this minus sign over here? When I want the operating potential of an electrochemical system, the operating potential, to be larger than the standard electrochemical potential for the system, I want E cell to be bigger than E0 cell. Do I want Q, my reaction quotient, numerically, to be bigger or smaller than 1? Smaller, you betcha. Which means, which follows from fundamental thermodynamics. For this system, for example, I want this concentration to be as large as possible and this concentration to be as small as possible, at least initially so. Because that will make Q considerably smaller than 1. And when you take the log of a number that's smaller than 1, you get a minus number. So you get a minus times a minus, which gives you a plus voltage to add to E0 cell, and that is the operating electrochemical potential. So really, we've talked about what's important in use and understanding of the Nernst equation. So we'll pick it up from this point next time.